Alright guys, so this video is going to be over lab 4, and basically I'm just going to try to talk through it and hit any main points. This might end up being a little bit of a longer video, but if you have any questions about lab 4 whatsoever, I would highly recommend you stick around for this. This is the first page, and the first thing that we're looking at here is this chart about ionization energy. And we'll talk a little bit more about this as we go through, but the thing that I want to point out here is that this is atomic numbers on the bottom, so atomic number 1, atomic number 2, atomic number 3. And if we look at the periodic table, we can sort of see a trend here. So here's atomic number 1, hydrogen. Atomic number 2 is helium, right? Then I'm going to go atomic number 3 all the way down here back to lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Neon is number 10, and that's, again, this really high ionization energy here. So this is number 10. And then we drop back down when we go all the way back over here. Ionization energy is, again, low here. So for sodium, number 11, this is our ionization energy here, very low. And then it's going to gradually sort of increase until we get, again, over to argon, number 18. So the high ionization energy here corresponds to argon, these things in group 8. As we've gone through, right, this lab portion, we filled out this column, this chart, and hopefully we started to see that the atomic numbers increase. The column/group numbers, those are going to be 1 through 8, and the column/group numbers, those are going to be what line up with the number of valence electrons. So if I go back to my periodic table, here I've got column 1. These species, these elements, will have 1 valence electron. Column number 2, these species will have 2 valence electrons. This is column number 3. So in this class, this whole middle section, we're sort of ignoring, right? We're not really going to be dealing with this whole middle section. This is what we call the transition metals. And for our purposes, we're more or less going to be just skipping over it. So column number 3, 3 valence electrons, 4 valence electrons, 5 valence electrons, 6 valence electrons, 7 valence electrons, and then over here, helium, neon, argon, so on and so forth. These have 8 valence electrons. They're in group 8. And these are what we call noble gases. They're not very reactive. So think about that. These things over here are not very reactive. Why might that be? Does it have something to do with their valence electrons? Probably, since I'm asking you that question. But think about that, right? So let's move on here. Here we're asked to draw models at the top of sodium and chlorine atoms. Sorry. Here's my model of my sodium atoms. I lost those for a second. Okay, so it says draw models of the sodium and chlorine atoms showing the number of electrons in each shell. So for sodium, I went ahead and did that already. And for sodium, that's going to be here, number 11, right? So that means I'm going to have 11 electrons. And I've shown sort of shell number 1 with 2 electrons in it, shell number 2 with 8 electrons in it, so 2 plus 8 is 10. So in shell number 3, I'm going to have 1 lone electron left over, okay? Now, later on, we sort of talked about, and I'm jumping ahead a little bit, this electron here being transferred to maybe a chlorine atom or something like that, and then that's going to end up giving us this Na+, right? So here, I'm down to 10 electrons, so 2 on the inner shell, 8 in the second shell, and this overall, right, is now going to have a +1 charge. So the charge on this overall is going to be +1. So this just indicates that this atom or ion now is going to have an overall plus charge. So, if you're at the point where you're looking at these pictures and you're comparing them to the periodic table and you're saying, okay, yeah, I understand, why there's only 1 valence electron here, how I'm getting this, filling pattern, 2 electrons here, 8 electrons here. I understand the transfer of the electron, how that's going to lead to an ion with a positive charge. If you're understanding all that stuff, great. If you're not, that's the stuff that you need to sort of figure out as we continue to move forward. All right. So I'm going to skip ahead to, let's start at this page. So here we're talking about the charges on ions. So for magnesium, for instance, magnesium is going to be here, right? And magnesium is going to have 2 valence electrons. So what's the easiest way for me to get to a full valence shell is to lose 2 electrons. And I think we've had a little bit of confusion here in terms of what does that mean. If you lose 2 electrons, right, let's go back to our sodium case. When I lose an electron, I go to a positive charge, right? So if I'm losing 2 electrons for magnesium, then I'm going to end up with a +2 charge, or 2+. For bromine, bromine's in group 7 valence electrons. So that means that my charge, right, to fill that shell, I'm going to gain 1 electron. So gaining an electron means I'm going to have an overall minus charge. Oxygen, 2-. Oxygen's in group 6, right? Group 6 valence electrons. How do I get to a full valence shell? I gain 2 electrons, 2- charge. And the last one here, potassium. Potassium is going to be in group 1, so that's going to be a +1 charge. Again, if you have any questions about how I did that, you need to figure that out. You need to come ask me, you need to ask your friends, or whatever you need to do in order to figure out how I came to that conclusion. Okay, now, this page, we're saying we've got, let's start here, we've got one, let's just do it like this, magnesium. How many bromines will I need to have in order to balance out the charge here? So whenever we're sort of putting our compounds together, we want to make sure that the charges are balanced. So here I've got magnesium 2+, and I want to know how many of these bromine I need in order to balance out the charge. So if it's 2+, I'm going to need 2 -1 charges, so 2 minuses, and now this overall thing has an overall neutral charge, right? If we go to the next page, now we're talking about these things that are called polyatomic ions. And it's a little confusing what these really mean, but I think the best way to sort of think about it, for us at least, is going to be just that that is an ion, so we can show it like this, and that overall thing has a 2- charge. I know it's confusing that there's 4 oxygens here, and we're thinking to ourselves, well, those oxygens should have -2 charge and things like that. But for these polyatomic ions, for our purposes, we're just going to treat the whole thing as having that overall charge. So at the bottom of this page, we're asked to figure out sort of the ratio between potassium and sulfate, so K and SO4. So if I just start, usually what I'll do is I'll just start with 1 and 1, so a 1-to-1 ratio, 1 potassium, 1 sulfate, and I'll say to myself, how do I balance this out? What do I need so that these will overall have a neutral charge? Well, hopefully it's pretty obvious to us that we're going to need 2 potassiums, right? 2 potassiums with a +1 charge, 1 sulfate with a -2 charge. And the way that we're going to write that would be like this. Usually we like to put the polyatomic ions in parentheses, and then this little 2 here in front of the K, that means I'm going to have 2 of these potassiums and 1 of these sulfates. So, if you're having any problems with this, let me know, and I will try to clear that up. But that's definitely where we should be at this point in time. All right, covalent bonds. So covalent bonds are different than ionic bonds because ionic bonds, we transfer the electron. So this would be our ionic case. We're going to transfer that electron, ionic case, we're going to transfer that electron away from the sodium. And in the covalent case, these electrons in our valence shell for chlorine, they're going to be shared, right? So here we've got chlorine. If I look at chlorine on my periodic table right here, 7 valence electrons. If I count these, 1, 2, 3, 4, 5, 6, 7. So these 2 electrons here, these are being shared, right? So total in the outermost shell, I've got 14 total electrons. 2 of them are being shared, and that way both of these shells can sort of be filled, right? That's how we get to our filled shell in this case, whereas previously we transferred an electron, ionic case. Here we're sharing the electrons. That's the key difference that we're talking about here. For this picture here, I just wanted to sort of show you this. We're going to start with a carbon, and in this picture, I'm not really concerned with any of the inner electrons. I'm only going to be showing the outer shell electrons. So I've got my carbon, and then here, where I've got shared electrons, that's where I'm going to sort of show that I've got a bond. So this line here that I'm drawing, showing between carbon and hydrogen, that is what we call a covalent bond between carbon and hydrogen. And I can know that that's going to be happening because I'm sharing those electrons between carbon and hydrogen. So likewise, these two electrons between carbon and chlorine will be my bond here. So wherever I have rectangles, that corresponds to my bonds. And then for chlorine, the last thing I'm going to do is I'm going to show my valence electrons. So that would be these two, and those two. So again, any inner shell electrons in these pictures, not really important. The valence electrons, right, those are the important, ones. And they're the ones that will participate in bonding, right? So this picture shows me all of my valence electrons. These two are shared, these two are shared, these two are shared, these two are shared, and then these are what we would call lone pairs of electrons. These would be represented by these pairs of electrons in chlorine's outer shell. All right. The last thing we're going to be talking about in this video is ionic and covalent materials. And this, page here is sort of setting up your experiment. And this picture here is telling us for the charge to flow, right, for this light bulb to turn on, we need to have ions, positively charged particles, negatively charged particles, in the solution that can move around. If this is the case, the light bulb will go on. So when we did the experiment, the only one that we found in this table that gave us light was table salt that was aqueous, that was dissolved in water. Sugar in water, or just pure water, we did not see light, right? No light, sad, no light, sad. But table salt was our aqueous solution. So we got to sort of figure out how that happened, right? How do we explain that? And the way that we explain that is that sodium chloride is Na+. It's an ionic compound, right? This is what we call an ionic compound. And sugar, this is what we're going to call a covalent compound. It's only held together by covalent bonds. So all of these lines here, right? That little line there, that little line there, all of these lines, those represent covalent bonds. And that's, again, where those electrons are being shared between oxygen and hydrogen, between carbon and hydrogen, between carbon and hydrogen, so on and so forth, right? These are all our covalent bonds, sharing of electrons. Whereas in our ionic compounds, that's going to be that transfer of electron that we talked about before. So in water, what's going on? We got to sort of explain this. If I have a lump of table sugar, I've got all of these sugar molecules all sort of one on top of the other, stacked together. When I put them in water, what's happening is that the water is separating out all of the little sucrose molecules. So I'll have these sucrose molecules floating around in the solution, right? That's what I would see. So again, I like to always imagine if you were a mini scuba diver and you went scuba diving, what would you see? You would see this fish, right, swimming around by itself in the solution. Now sodium chloride's a little bit different, right? So here, let's go ahead and build our sodium chloride lattice. So all right. So here's what, our table salt will really look like. I would have all of my sodium and chlorine atoms arranged, right next to each other. And so this would be sort of like salt, right? This would be what it would look like if I had a salt molecule. Now, when I put this in water, so here I've got some water molecules coming in, what's going to end up happening is that these water molecules will start interacting, right, with these ions. So, let's maybe do this one down here. These water molecules will start coming in, start interacting, right, with this ion, and it will literally pull this away, right? So here I'm going to have my sodium, and it's sort of being surrounded by these water molecules, and this is going to be able to leave, right? And that same thing is going to happen to all of these. So in solution, I'm going to end up with individual ions, right? So if you went swimming in this and you did the scuba diving experiment, you would see sodium ions floating around individually, surrounded by water molecules, and you would also see chlorine atoms floating around, surrounded by water molecules. And I'm showing just 3 water molecules here, but it could be more, right? But this just gives you an idea of what that solution is actually going to look like. So if you did that, you'd see these ions floating around. The fact that we have these ions floating around, that allows the electricity, right? That allows for the light bulb to light up. So that's what's going on in that case. So then the next question is, in which cases do any ionic bonds break, right? So going back to our experiment here, our ionic bonds are breaking when we dissolve it in water, but our covalent bonds, those are not breaking, right? The intermolecular forces between this sucrose molecule and another sucrose molecule, right? Those are breaking. So if my hands are sucrose molecules, when I put it in water, they're going to be separating, right? But this whole molecule is staying intact. Almost done here, guys. So this whole thing here, what it's really getting at is that it doesn't really make sense for us to talk about a sodium chloride, species as its own individual molecule, right? Because in a solid, it's going to be this big giant lattice that there's, could be any number of sodium atoms and any number of chlorine atoms, right? They should probably equal each other out, but it could be bigger, it could be smaller. Once we put it into solution, right, these are going to separate. So we're never really going to be able to isolate just one individual sodium chloride molecule. So this question here, question number 2, if we define a molecule as an arrangement of a specific number of atoms, that doesn't really make sense for our sodium chloride. We don't really call this a specific molecule. This would be more what we would say is an ionic compound, or when we put it into water, 2 separate ions. That's a little bit different than our covalent case, right? Because our covalent case, it is going to be this whole molecule, and we can isolate one of these molecules. We would see this whole thing in the solution. All right. The last page, according to this molecule, is there a difference between an intermolecular bond and a chemical bond? Yes. So this dotted line, that is our intermolecular bond. That's the attraction between these 2 molecules. And then the chemical bonds, right, these are going to be our chemical bonds in between the 2 atoms in the molecule, right? So in this chloromethane, there's going to be 4 chemical bonds between those atoms, and we've got 1 intermolecular bond here. According to the model above, does it make sense to call chloromethane a molecule? I would say yes, right? We can isolate this one specific thing that is a molecule of chloromethane. All right, now the last thing I'm going to say before this video is over is ask questions. So in class, we've been doing a great job of asking questions, but really the more efficient way to do that, and I'm going to be harping on this as we continue this class, is to ask questions outside of class so that I can prepare more, nice, clean answers that are more efficiently distributed to you. So in-class questions are great, but I think for efficiency's sake and to keep everyone on the same page, out-of-class questions is what you guys need to work on. All right, more videos to come.